Next, we're going to talk about a class of reactions called substitution reactions. Let's take a look at an example of such a reaction. Here we have hydroxide reacting with chloromethane, and our product has, where the chlorine used to be on the carbon chain, we've replaced it now with the OH group, and the chlorine is now on its own as chloride. So this is described as a substitution since we have replaced one group with another group. We've substituted. And let's define some of the players in this reaction. This first species I've labeled NU ... That stands for nucleophile. So I'm going to be using the abbreviation NU with a lone pair. And a nucleophile is defined as something that is electron rich. So typically we'll see a lone pair on a nucleophile. We'll also see examples where a pi bond can behave as a nucleophile. It can have a negative charge, like our nucleophile in this case is hydroxide, we see a negative charge. But a very nice abbreviation for nucleophile is NU with a lone pair. That lone pair right away gives you some clue as to the behavior of this nucleophilic species. And because it's electron rich, a nucleophile is going to be seeking an electron deficient species. The next part in this reaction is described as the electrophile. A very handy abbreviation for electrophile is E+. Again, that kind of tells us something about the species because electrophiles are things that are electron poor. Now, it might be possible that you'll see a positive charge to show the electron deficiency, or more likely what we'll usually have is a partial positive. And that's true for this electrophile here. It's a neutral species, there are no charges, but because this chlorine is pulling electron density away from the carbon is in fact partially positive, and that's what makes him a good electrophile. An electrophile is something that seeks an electron-rich species. Oh, I should mention, where does the name electrophile come from? It's called an electrophile because it is electron-loving. Right? And that makes sense. If it is electron deficient, it's going to be seeking electrons, loving electrons. A nucleophile is called such because it is nucleus loving. And what sort of things do we have in the nucleus of an atom? We have protons. We have positively charged species. So a nucleophile is something that is seeking out electron deficient species, and electrophiles are something that are electron deficient, seeking out electron-rich species. So what we have here with the nucleophile-electrophile pair really is just a perfect match. And we're going to see that nucleophiles and electrophiles coming together are going to explain the vast majority of the organic reactions we're going to be seeing down the road. Now, the other part in this equation is, in this case, played by the chloride. It's called the leaving group, and which I'm just going to abbreviate LG. Sometimes it's just abbreviated with an L. And this, as the name implies, is a group that leaves, and as it leaves, it takes its 2 electrons with it. So you can see that this bond ended up leaving with the chloride because now it has 4 lone pairs of electrons. And that's going to be true of all of our leaving groups. They'll take electrons with them. And we're also going to be learning about what makes a good leaving group. We'll find that stable groups, things that are stable on their own, would make very good leaving groups. And things that are weak bases are typically pretty stable. So we'll look for those sorts of features. So a general reaction, and I should also mention that this leaving group we had here is a chloride. So for example, X- makes a very good leaving group. We'll see chloride, bromide, iodide as a very common leaving group that we can have, and these are all weak bases because it's conjugate. If you look at HCl, how do we describe HCl? We know that as a strong acid, and so that tells us that the conjugate base chloride is a very weak base, very stable, and so they make very good leaving groups. So overall, the general reaction for the substitution reactions we're going to be studying in organic chemistry look like this. We have some kind of nucleophile reacting with some kind of carbon chain. This R represents a carbon chain that has a leaving group on it, and when the reaction is done, that R group is going to have the nucleophile bonded to it in place of the leaving group, and the leaving group is going to now be on its own, and typically with an extra lone pair and a negative charge. So if this is our general reaction, what are some things we can study about it? Well, what if we wanted to understand the mechanism by which these starting materials get converted to these products? What are the possible mechanisms for a substitution reaction? Well, there's really two reasonable possibilities. One possibility would be a simultaneous mechanism, or in other words, a concerted mechanism, in which the nucleophile attacks the carbon, starts to form the bond with the carbon group at the same time as the leaving group leaves. That would be just a single-step mechanism that would accomplish the transformation. And this mechanism actually does exist. We'll be studying this. This mechanism is called the SN2 mechanism, a simultaneous concerted single-step mechanism. Okay, but another possibility is that we have a stepwise mechanism in which the leaving group leaves first. Now, if the leaving group leaves, what does that leave behind on this carbon? This carbon is now missing a bond, so this would end up being a carbocation. And then that carbocation could combine with the nucleophile to give our substitution product. And in fact, that mechanism happens as well. This mechanism is known as the SN1 mechanism. So we're going to be learning both about this concerted mechanism and this stepwise mechanism, and they're called the SN2 and the SN1. We'll start with the SN2 mechanism, and here's an example of such a mechanism. We said this is the one-step mechanism. So what does it look like? We could show arrows to follow the electron path, the electron movement, and the bonding. Our nucleophile, I'm sorry, we should label these guys. This group that is coming in and doing the substituting we describe as a nucleophile. Here again we have something that's a lone pair and a negative charge. The alkyl halide here is going to be our electrophile. Now again, why is it electrophilic? I don't see any electron deficient species. Well, sure, that carbon bearing the leaving group, bearing the halogen, is in fact partially positive. So there is going to be an attraction between this electron-rich nucleophile and this electron-deficient carbon, and that's what's going to help form this bond. As that bond is formed, this carbon-iodine bond is going to break, and those electrons are going to go to the iodide. And so there's our mechanism, just two arrows, single step, and we get our two products. This is our substitution product, and this is our leaving group. Remember, we labeled him the leaving group. Now, the direction of attack of the nucleophile onto the carbon bearing the leaving group is described as backside attack. The nucleophile has to come in from the opposite face of where the leaving group is. That's the only possible attack to get that leaving group to leave and have the orbitals interact properly. So we're going to see the consequences of that shortly. Okay, let's talk about the kinetics of the reaction, things that affect the rate of the reaction. The rate of the SN2 is given by the following rate expression. The rate is proportional to both the concentration of the methoxide, the CH3O minus, the CH3O minus, our nucleophile, and the concentration of the ethyl iodide. Let's just abbreviate this. CH3CH2, we could abbreviate that as ethyl, ET for ethyl. So in other words, in the rate expression, we find both the nucleophile and the electrophile. That's why this reaction is described as a bimolecular reaction. You add up the exponents. Each of these are to the first power. So it is a bimolecular reaction, and that's where the SN2 comes from. That's what the 2 represents in the name, is that it's the bimolecular reaction that has both the nucleophile and the electrophile coming together in the one step of the reaction. Now we'll find that sterics play a big role in the rate of the SN2, so let's see some examples of that. How about if we study this SN2 reaction where we have an alkyl bromide, so we have our leaving group here, and let's use cyanide as our nucleophile, and take a look at this substitution reaction where the cyanide has replaced the leaving group to do an SN2. If we vary the type of alkyl group here, the type of R group we have, we can measure the rate and see what effect that has on the rate of the reaction. So here are some different R groups that we can have. This first one where it's a CH3, we would just describe that as a methyl group. It's handy to take a look at some abbreviations that organic chemists often use. MEBr represents methyl bromine, so CH3Br could be a shorthand notation, could be MEBr. And how about this one? If we have 2 carbons, that's now an ethyl group, so a common name for this would be ethyl bromide, and abbreviation could be EtBr. And how would you describe this the type of carbon bearing the leaving group? Well, we could use terms like primary, secondary, tertiary to describe the number of carbons attached to that carbon. Because this carbon has just one carbon group attached, it is a primary carbon. The leaving group is on a primary carbon for ethyl bromide. How about this next one? What do we call the group when you have a 3-carbon chain and you have an attachment at the middle carbon? That's one of the common names for the propyl groups. This is the isopropyl group. So a common name for this would be isopropyl bromide. And isopropyl bromide is a nice example of a secondary carbon bearing the leaving group because this carbon has 2 carbon groups attached. And our next one is a great example of a tertiary carbon. Right, this carbon bearing the leaving group. So right here is where we're imagining our leaving group is. Has 1, 2, 3 carbons attached, and what do we call this arrangement of 4 carbon atoms? This is called the T-butyl group. So we could also run this reaction using T-butyl bromide. What's happening is we're moving down this this column, down this list, is we're steadily replacing the 3 hydrogens on this carbon with more and more and more carbon groups. What we're doing is we're increasing the steric hindrance. Now this last one is kind of an interesting molecule. How would you describe the carbon bearing the leaving group here? Looks like it's just a primary carbon, right? Because there's just one carbon group attached. But what's interesting about that carbon group that's attached? It's a tert-butyl group. So even though it has just one group attached to it, it's a very bulky group, and so this is also a really sterically crowded center. This is called it's not really just a simple primary. This is known as the neopentyl group. That's another common name. And the neopentyl group is kind of uniquely known because of its large amount of steric hindrance. Okay, so let's take a look at the rates of these SN2 reactions. If we describe the primary carbon as having a relative rate of 1, it turns out that the methyl bromide reacts 30 times faster. So really fast SN2 when you're attacking just a methyl group. By making it a secondary, it slows it down. When making primary, it slows it down. When you make it secondary, it now goes to 0.02, so it's 50 times slower by having isopropyl instead of ethyl. And when you go to tert-butyl, our number becomes approximately 0.0004. So now we're looking at a reaction that's so slow, it's barely measurable. Okay, and how about neopentyl? Neopentyl is even slower, actually. There's 1, 2, 3, 4 zeros, and then a 1. So what we've done is we've increased the branching on the carbon bearing the leaving group. We describe this first one as having alpha branching because the branchings occur at the same carbon as the bromine. And for neopentyl, we don't have any branching at the alpha carbon, but right away on the beta carbon, the very next carbon over, if we lettered these, we have branching. And so this effect is due to what's described as beta branching. Okay, but clearly both of these are very sterically crowded, and we see that we definitely have a decreasing rate as we move down this list and increase our steric crowding. Okay, let's take a quick look at just some extremes here. Now, these stick models don't really do justice to the system because it seems when we just represent the electron cloud with this skinny little line, it seems like there's plenty of room, okay? But remember that these are all clouds of electrons, and when you look at a space-filling model, you can see a much better picture on why these are there's such a big difference in steric hindrance. So make sure you take a look at some of those illustrations. Okay, so this would be an example of methyl bromide. There's a bromine, 1 carbon, and just 3 hydrogens attached. The nucleophile coming in has to come in from opposite the bromine. This is what we call backside attack. So when you view the molecule from the backside, you see that all we have are hydrogens here, very accessible, very easy for the nucleophile to approach. Okay, if we compare that to a tert-butyl group has replaced those 3 hydrogens with 3 other methyl groups, each of which is tetrahedral. And so now, and once again, in this model, you don't see it quite as dramatically as if the space-filling model. But clearly, when you try and come in here, you're now going to experience some steric hindrance, some steric crowding, something blocking the nucleophile trying to get in here. And even with the neopentyl, if the crowding is right here, you get that same effect. In a space-filling model, when you show the actual regions of electron density for these bonds, you can't even, the carbon that you're attacking isn't even visible. So huge steric hindrance for the tert-butyl. We could maybe draw that out here. I've shown the tert-butyl group here, trying to show how each of these carbons is tetrahedral, so they're projecting out in all directions, and so my nucleophile is trying to get in from this direction, from the back side, but it's experiencing some steric hindrance from the methyl groups that are attached to the carbon. So that's a way that we could show it. We could describe it as having a crowded backside approach. And that's going to be true for both the tertiary and the neopentyl. So overall, the rate of the SN2, by considering the type of the alkyl halide, the fastest that we have, the best SN2, that's the best, that's the quickest is going to be when you have a leaving group on a methyl carbon. And that's the faster than primary, that's faster than secondary. And actually, we have this huge rate increase. Let's make this a double arrow, double less than here, or greater than. There's a huge jump in tertiary neopentyl. And the fact that these are so slow that we actually consider them usually to be a no reaction. It takes so long for any amount of it to react that it's just, we describe it as having no reaction at all. Okay, so we'll keep that in mind when it comes to backside attack. Okay, this rate based on sterics and tertiary and neopentyl are going to be so slow that we say no reaction. How about an energy versus progressive reaction diagram for an SN2 reaction? What would that look like? Let's come back to our example here of this substitution reaction. Well, it's just a one-step mechanism. So a one-step mechanism starts at our starting materials. We can put them at some energy level. And then when we go to draw the energy level of our products, typically our products are going to be lower in energy. That's what makes a substitution favorable, and we'll actually talk about that today on what makes a substitution a favorable reaction. And then when it's a single-step reaction, we just have a single transition state to go through before our starting materials go to products. Okay, so it looks kind of like a typical single-step mechanism that's going to be endothermic. We could, well, let's take a look at this transition state a little more closely that I just labeled up here as TS. Remember, a transition state is something that it's a high energy species. Sometimes it's called an activated complex, where you're starting to form bonds, you're starting to break bonds. So what's characteristic of a transition state is partial bonds, partial charges. And we know that our mechanism is this. Our oxygen is attacking the carbon in the process of breaking the iodide. So what does it look like in the meantime? Well, how we can represent that bond that's being formed between the carbon and the oxygen is as a partial bond. Partial bond. One that is being formed. In this case, this is a bond forming. And what do we have on the other side? We have this carbon-iodine bond that is on its way out. So this is also a partial bond because this is a bond that's breaking. So we represent both forming bonds and breaking bonds with a dashed line, a partial bond. Now what happens to these three groups? We have a hydrogen and a methyl. You can see it tetrahedrally. They're pointing all off in one direction now. But in the product, notice they're pointing all off in the other direction. We're going to look at that stereochemistry in just a second. And what happens in the transition state is they're going to be kind of all planar to each other. They're all going to be flattened out as they transition from one direction. They're going to go planar, and then they're going to go in the other direction. So this is a good looking transition state, but let's take a look at the charges that are going to be developing or dissipating in the transition state. We see that in our starting material, our oxygen here is negatively charged, but in the product, when it's bonded to the carbon, it's going to be neutral. So what does it look like in the meantime, in the transition state? It's going to be somewhere between -1 and 0, so we describe that as a partial minus. A delta minus means we have a partial charge. Are there any other partial charges? Sure, the iodine starts out neutral and it ends up with a negative charge in the product. So now this is going to be between somewhere between 0 and -1. So we'll put a partial minus on this iodine as well. So this is a pretty good looking transition state, partial bonds, partial charges, and that's what we'll have to fill in our energy versus progress of reaction diagram. Now let's think about this transition state and consider its implications in the kinetics that we just learned about. The fact that sterics, right? If the carbon bearing the leaving group is too sterically hindered, what effect is that having on the reaction? Well, that means that these, instead of a hydrogen and a carbon, let's say all three of these were carbons, it was a tertiary carbon, that's going to have a lot of steric hindrance, that's going to have a lot of crowding, and that's going to take that transition state energy and raise it up. What does that do to reaction? It slows down the reaction because it has a higher energy of activation. So the transition state energy is higher in energy, and the energy of activation is higher, therefore, and so the reaction is too slow. So this transition state is going to explain the rate effects that we just saw in the previous slide. Let's also consider what the hybridization of this carbon looks like. This is kind of a strange carbon, isn't it? It looks like it has 5 bonds. So what kind of, we saw sp2, sp3. What do you expect if you have 5 bonds to carbon? Is this sp4 hybridized? There's no such thing. That doesn't exist. Okay, and in fact, carbon can't have 5 full bonds. We know it can't accommodate that because that would violate the octet. Okay, so instead, what arrangement have you seen for a carbon that has 3 groups that are planar, and then something else that is perpendicular to that plane? Kind of looks to me like it's sp2 hybridized. And in fact, if we draw that picture, if we replace those simple partial bonds and charges with a p orbital, we can see how it is that this carbon can accommodate both the incoming nucleophile and the outgoing leaving group. So an sp2 hybridized transition state accounts for that very nicely, and that's what's happening as we're starting to form one bond and starting to break the other. Now, knowing that there is a p orbital that develops on the carbon that's undergoing the SN2 also explains another observation we see for the SN2 reaction. We find that the presence of a neighboring p orbital, conjugated p orbitals, would be good for the SN2. For example, if you had an allylic leaving group, the word allylic means that you're next to a pi bond. So here we have a carbon that's not on the double bond, it's next to the double bond. This allylic leaving group would be a great SN2. This center, this allylic center, is a very fast, very favorable SN2, and that's because right next door to this carbon that's going to have a p orbital in the transition state is another p orbital and another p orbital, and so you can get delocalization, you can get some resonance energy, some stabilization because of that. So we'll take a look at those SN2 reactions. Occasionally we'll see that if the leaving group happens to be a allylic one, that's very favorable for the SN2. Let me take a quick look back to our energy versus progress of reaction diagram. So we said this is what our transition state looks like. And let's imagine now if we were to have a more sterically crowded carbon bearing the leaving group. Right? Maybe if this is, let's say this is a primary alkyl halide. What if you had a tertiary alkyl halide? Well, that transition state is now going to be higher in energy for a tertiary alkyl halide, and so the path leading up to that would be much harder. And in fact, for tertiary, it's typically going to be so high that it prohibits the reaction. It's so slow, we say it is no reaction. And how about if our leaving group was allylic? Then instead of being here, that's going to be something that stabilizes the transition state. So that might be what we find if we have an allylic leaving group. And so what effect would we see? That would speed up the reaction. So the SN2 would be a faster reaction if it was allylic. So I just wanted to kind of point out that what we're looking at are kinetic effects here. These are things that affect the rate of the reaction. Something that either destabilizes or stabilizes the transition state is going to affect the rate. One more thing to discuss about the SN2 is the stereochemistry of the SN2. We said that it's backside attack. The nucleophile is to come in 180 degrees from where the leaving group is located. The result of that is we get what's known as an inversion of stereochemistry. We say inversion takes place. And let's consider this chiral carbon has 4 unique groups on it. If our nucleophile comes in to do an SN2, we know it has to come in from this direction. And so it's going to be coming in from the left. And when it comes in and forms a bond now, it's going to be staying on the left. It's still going to be bonded on the left. And what's going to happen to these 3 groups that were on the right? I think I'm mixing up my directions here. On the left, they're going to go up and become flat, planar in the transition state, and then they're going to come down to be in the other direction. So it's kind of like you have an umbrella. If you think of these 3 groups as forming an umbrella, you're going to straighten them out, and then it's going to flip in the other direction in the product. This is only observable. This happens every time you do an SN2, but it's only observable when you have a chiral carbon. So if there were 2 hydrogens on here, if this was a symmetrical carbon, you would not be able to see that an inversion has taken place. You would have no experimental evidence for that. Okay, now this SN2 usually changes the configuration as a result. So in other words, if you started out with the R configuration, you would now have S, and vice versa, and S would end up R. Okay, now I say usually, that's not always true, because this assumes that the 4 groups you prioritized in the beginning have essentially the same priorities in the end. So, and that's most often the case. So for example, if your leaving group is priority group number 1, which it very often is if it's a halide, and the nucleophile coming in is also a priority number 1 compared to the others, then absolutely your R is going to get converted to an S, or your S is going to get converted to an R. But because this prioritization has to be redone with the new 4 groups on the product, there's some times where you'll find an exception to that, and your configuration happens to come up with the same name when you do it. So let's see an example here. We can see this when our leaving group is on the right and the nucleophile is on the has to come in from the left. How about in this line drawing? In this case, our leaving group is a wedge, and so that means it's projecting out towards you. So what does backside attack mean? Backside attack means it has to come in from behind the board and attack from behind, which means the nucleophile is going to end up being bonded in the back position. So when my nucleophile comes in, it has to approach from behind the board, and it's going to end up as a dashed bond as a result. So we might see the inversion as a left to right. We might see it as a wedge going to a dash, or a dash going to a wedge. Those are the sorts of different ways that we can observe this inversion of stereochemistry. Let me just throw in the hydrogen here. With our line drawing, a lot of times we leave off the hydrogen. And I know the hydrogen is still here. It must be a dashed bond in this position right behind the chlorine. So what happens to that hydrogen now in the product? It can't be a dash anymore. Now again, it's like it's like the umbrella it's flipping. The hydrogen was behind, but when the nucleophile attacked, the hydrogen straightened out, and then it flipped forward, and there was your inversion. So the hydrogen, as a result, will now be in a wedged position. So there you can see the inversion of stereochemistry again. So let's summarize what we know about the SN2 reaction. This is the one-step mechanism. We describe it as backside attack. So my one step is my nucleophile attacks the carbon, kicks off the leaving group. That's it. One step, one concerted process. That backside attack results in inversion of stereochemistry. And what are the things that are required for the SN2 where maybe we could predict that an SN2 is going to happen? Well, we need an unhindered leaving group, or electrophile. The carbon bearing the leaving group has to be unhindered in order for that backside of the carbon to be available. The leaving group has to be on a tetrahedral carbon. So, when we're picturing this inversion of stereochemistry in the backside approach, it's implying that we have a tetrahedral carbon. This is for alkyl groups to undergo SN2s, SN3, SN2s, and it has to have a good nucleophile. If the nucleophile is going to be coming out and attacking the carbon and displacing the leaving group, you have to have a pretty aggressive nucleophile to do that. So we're going to talk about what it means to be a strong nucleophile shortly, and you most definitely need a strong nucleophile in order to do the SN2 reaction. And the rate, remember, once again, that this is based on sterics. And our fastest then is going to be the methyl. That's the best SN2, that's great. And our slowest is going to be the tertiaries. Tertiary is so slow, you should just go ahead and say no reaction. If you ever find yourself doing an SN2 mechanism on a tertiary center, you're probably making a mistake. You need to back up and think about something else. Let's go through some examples of SN2 mechanisms to see if we can predict what the product is going to look like. So we'll start by looking for a nucleophile and an electrophile. I see my alkyl halide here. There's my leaving group. So once I identify my leaving group, that tells me I have my electrophile, my E+. Remember, it's the carbon bearing the leaving group that's partially positive. So where do I have a potential nucleophile? Right here. Ammonia is actually a great nucleophile. This nitrogen has a lone pair. And because it's just a single-step mechanism with two arrows, I always recommend drawing that mechanism as part of your predict the product exercise, because that's really going to help you draw the product more accurately. So it looks now like we've formed a new bond between the nitrogen and the carbon. So you can put the hydrogens on either side here. I just wanted to clearly show the new nitrogen-carbon bond. I've kicked off my leaving group. I have Br- here. Some instructors really emphasize showing that leaving group after it leaves, but for others, they're more interested only in the organic product, what happens to the carbon chain as a result of the mechanism. And looking at this product, it looks a little strange to me, because when I look at this Lewis structure, something doesn't look like a typical configuration. I think it's this nitrogen, right? Usually nitrogen likes to have 3 bonds and a lone pair to be neutral. So I better check this formal charge. What do we have for this nitrogen? It has 1, 2, 3, 4 bonds, 4 electrons, and nitrogen wants 5. So it's missing an electron. So actually this is an N+. So it's possible in certain cases to get charged products after an SN2, especially with things like amines. They love to do the SN2. So they would give this ammonium salt as a product. Okay, how about the next one? Do we have a leaving group? Can we find a leaving group? There it is. Our iodide is the leaving group. So here's our electrophile. Sodium hydroxide, NaOH. As soon as I see that sodium in there, that means I have an Na plus and O-. So the sodium plus is just a spectator ion. We could just scribble him out and stick with just the hydroxide. I know the hydroxide is the species with the electrons. That's going to be doing the reaction. So I have hydroxide as a nucleophile, has a lone pair. That's what we're looking for as a nucleophile. We have our leaving group. What kind of carbon is the leaving group on? How would you describe this carbon? This has 2 carbons attached, so it's secondary. Anything else about this carbon? It's also next to a pi bond, secondary allylic. Looks like this would be a great SN2 to take place. Secondary is okay. Allylic makes it even better. So what's going to happen is this is going to attack the carbon, kick off the leaving group, and then finally tell me about the stereochemistry of this attack. How is that hydroxide going to be approaching the alkyl halide? Well, in this case, because the iodide is pointing away from us, the hydroxide, the nucleophile, has to be coming in from the top of the page, and that's where it's going to end up being bonded. So the hydroxide will be a wedge. There's where we see our inversion of stereochemistry, and that looks like a good SN2. How about the next one? How would you describe this first structure, the bromide? This looks like an electrophile. So we have our leaving group here. KCN, again, any formula with potassium in it must be ionic. So what we have is CN minus. So this is also a very good nucleophile that we should get familiar with and be used to seeing. Okay, and so he loves to do the SN2, but tell me about this electrophile. Does this electrophile love to do an SN2? How would you describe the carbon bearing the leaving group in this case? This carbon has 1, 2, 3 carbons attached. How would you describe that? We describe that as tertiary. What happens on an SN2 on a tertiary center? Nothing happens. No reaction because we have a tertiary RX. Okay, so we really have to know all those details about the SN2 in order to accurately predict the product. How about our next ones? This is NaOCH3. So once again, that means I have OCH3 minus. That looks like you'd be a good nucleophile. It looks pretty similar to some that we've seen before, kind of like hydroxide. It's got an O minus. We've got a leaving group here on the chlorine, and as the chlorine. And how would you describe the carbon bearing that leaving group? Would you describe that as a secondary carbon? It's got 2 carbons attached, or is it something different than that? Yeah, it's actually on a benzene ring. So we call this an aromatic, AR for aromatic leaving group. Or vinyl is just kind of a general way to describe a leaving group or something that's directly attached to a carbon-carbon double bond. And how could I do backside attack on this molecule? I would have to be coming in through the plane of the benzene ring in order to do that backside attack. It's impossible. Okay, so this is no reaction because we have an sp2 hybridized sp2 carbon that the leaving group is on. And so we need to remember that SN2 reactions take place on ordinary alkyl groups, sp3 hybridized carbons. Okay, and finally, this last one is quite interesting. We have hydroxide again, very good nucleophile. And so you might think that he can come over here and attack and kick off the leaving group, right? That would be an SN2. And that reaction certainly is reasonable, but there is a second reaction that can take place here. Because hydroxide can not only act as a nucleophile, this is acting as a nucleophile, it would be attacking a carbon and kicking out a leaving group, but it can also act as a base. And do we have any protons on this structure that might be reasonably acidic? Look here, we have a carboxylic acid functional group. We know those are pretty good acids. And so what happens is instead of doing an SN2, we're going to do the very, very fast acid-base reaction instead. So if an acid-base reaction is ever possible, is ever something that can be considered, that's what's going to happen first. So let's consider that first. In other words, the hydroxide is going to go after this proton. That's what it means to be a base. It's going to remove that proton. And what does that leave behind? Let me redraw this as an O minus, and then we have a CH2, 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 and then a chlorine. Now I'm redrawing this because I want to illustrate something. I'm redrawing as a line drawing because I want to illustrate that what we have now is an O minus. That's a nucleophile. In the same molecule as we have a partial plus down here, this is an electrophile. And do you think it might be possible for an intramolecular reaction to take place where a nucleophile and an electrophile that are tethered can come around and react? It is possible. So we would describe this as an intramolecular SN2 or backside attack, an intramolecular backside attack where my O minus attacks the carbon, kicks off the leaving group. And what size ring do we just form? We're going to form a ring every time we do an intramolecular reaction. Oxygen is 1, 2, 3, 4, 5. We just formed a 5-membered ring. So we could draw a very nice 5-membered ring. Oxygen is 1, 2, 3, 4, 5. And intramolecular reactions, SN2s in this case, are very favorable reactions. Very favorable, especially entropically, because we don't have to worry about bringing the nucleophile and electrophile together. They're already together. They're already tethered. So the likelihood that they're going to collide and react is very high. So, so these are very favored reactions. They are favored when we're forming either a 3 or a 5 or a 6-membered ring. And for the most part, only those size rings are going to be easily prepared this way. Okay? Why are 5 and 6-membered rings good? Because they have so little ring strain. We took a look at those structures. We saw that they're very stable. They're a little flexible. So it's very easy for those the ends of that carbon chain to come around and have those two meet. Now a 3-membered ring we know has a lot of ring strain, but because the nucleophile and the electrophile are so close, they're so closely aligned that it's impossible for them not to react. It's a very rapid reaction, very easy to happen. But a 4-membered ring now, you're further apart, and so now trying to bring them together is not going to be able to overcome that ring strain. And if it's a 7-membered ring or larger, now these nucleophile and electrophile are so far away that it's going to be kind of hard. They're flopping around. It's going to be difficult now for them to come together, and those reactions are usually disfavored. So 3 or 5 or 6-membered rings are things that we'll keep an eye out for, and that's when we have, within the same structure, we have a nucleophile and we have an electrophile. So let's take a look at another mechanism. We saw the SN2 mechanism, single-step substitution mechanism. Let's consider the following reaction. Here we have another nucleophile with an O-. We have a carbon bearing a leaving group, so this would be an electrophile. An alkyl halide could act as an electrophile. And we had a leaving group leave, and in the place of that leaving group we have that nucleophile. So is this a substitution reaction? Looks exactly like a substitution. We have a nucleophile replacing a leaving group. Could this be an SN2 mechanism? Could this follow the mechanism that we just studied, the one-step mechanism? Backside attack, where the nucleophile attacks the carbon, kicks out the leaving group. Does that seem reasonable in this case? It doesn't. No, it cannot be, because what kind of carbon is bearing the leaving group? It's a tertiary carbon. We have a tertiary alkyl halide. Okay? So it's still a substitution. Overall, we still get a product where our leaving group's been replaced by a nucleophile, but it must have a different mechanism. There must be a different path taken to go from the starting materials to the products. And that second mechanism is known as the SN1 reaction. That mechanism is called the SN1. I think I just remembered I forgot to define the SN2. The S is substitution and nucleophilic, just like the S and the N in the SN2. We have a nucleophilic substitution reaction, but in this case it's unimolecular. The SN2 is bimolecular. The SN1 is going to be unimolecular. Let's see what that looks like. Okay, so how can we go from these starting materials to these products without doing it in a single backside attack? Well, there's going to be always at least 2 steps. We'll see a little later that there's very often a third step. But here's what happens in this stepwise mechanism. The first thing is loss of our leaving group. So our leaving group is just going to pick up on its own and be lost. So I can show my Cl- here. And now what happens to this carbon? This carbon just lost a bond. So there's going to be some kind of charge associated with that. It's got 1, 2, 3 for its electron count. Carbon wants 4. So this is going to be a C+. It's going to be a C+. We call that a carbocation. And we're going to get a carbocation. That's not our final product. So this is known as an intermediate because it's formed in the reaction, but then it's consumed right away. Because that carbocation is going to continue reaction. And our second step, step 2, is addition of our nucleophile. So our nucleophile is going to come in here. Our O minus. Do you think this carbocation would be a good electrophile? I think it'd be a great electrophile because it's super reactive. It's missing its octet. It's got a full positive charge. So this is most definitely electron deficient and looking forward to reacting to a nucleophile. So this reaction would be a great one where the nucleophile attacks the carbon. And now that carbon gets its 4th bond back, so it's neutral. The oxygen has 2 bonds, so it's neutral. And there's our product. Okay, so we've achieved our products. We've made the chloride and the substitution product, but we did it in this 2-step process. Now, when you have a multiple-step reaction, we try and identify what the rate determining step would be. Which of these 2 steps is the rate going to depend on? And when we compare the 2, I would describe this first step as a very slow step, very difficult, and that would be what determines our rate then, while the second step is very fast and easy. So what is it about this first step that makes it endothermic, that makes it something that you have to climb uphill? Well, I mean, we're going to a very unstable carbocation intermediate, so that's one clue. And the other thing is that you're breaking a bond. The process of breaking a bond is always an endothermic one. You always have to put energy in to break a bond. So we go uphill for this step, and then this second step is a piece of cake. The nucleophile is going to love bonding with the carbocation. It satisfies both parts, and you get to form a bond. Bond formation is an exothermic process, so you release energy here. So once we form the carbocation, it's very easy for the species to continue on to product. So how would we define the kinetics, and what can we tell about this reaction? Well, like we said, this is good. It's going to be dependent on just this one step, this rate determining step, and what's involved in that step. All we have is the alkyl halide, T-butyl chloride in this case, losing the leaving group. So it turns out that the rate for the SN1 is dependent only on the concentration of the T-butyl chloride, or the T-butyl chloride in this case, or the electrophile in general. So the rate determining step involves the electrophile only. That's why this is called a unimolecular reaction. That's for the SN1, where the 1 comes from. And it's observed that the rate is independent of the nucleophile. So it doesn't matter how much of that nucleophile you had around. You could double the amount, triple the amount. It has no effect on the rate because we're just waiting for that leaving group to be lost. That's the only thing that defines the rate. What will really have a big impact on the rate, though, is that a more stable carbocation will be formed faster. So we're going to look for systems where we can get good carbocations being formed. And if the carbocation is formed faster, that was our rate determining step. So what does that tell us? We have a faster SN1 as a result. So what do we know is a good carbocation, is a stable carbocation? Well, things like benzylic, allylic, tertiary, those are all very stable carbocations. So because they are stable carbocations, they're going to be fast SN1 reactions. They're going to, when I put a leaving group in one of those positions, it's going to very readily undergo this substitution mechanism by this reaction. Secondary is okay. That's still a good carbocation. But when we got to primary or methyl, those were very, very high energy carbocations. And because those are unstable carbocations, we describe that essentially as having no reaction for SN1. Again, it's really a kinetics effect because it is so slow, we describe it as no reaction. If you find yourself forming a carbocation in a primary carbon or a methyl carbon and having no place for it to go, other place for it to go, you're probably moving in the wrong direction, and there's probably a better solution that you should consider. So how about the energy versus progress of reaction diagram for this reaction? We're starting, again, at some combined energy for our starting materials, our nucleophile plus our alkyl halide. And when we're all done, our products are going to have some combined energy that will typically be lower in energy because if it's a favorable substitution reaction. But it's no longer a single-step reaction, and it's at least 2 steps, because what we're going to be doing is we're going to be going through this, this intermediate, which is a carbocation. So step 1 is we're going to go from our starting material to our intermediate, and step 2, we're going to go from our intermediate down to our product. Now, as usual, for every step, you need to go through a transition state. So this is transition state 1. And then going from the carbocation to the product, again, you go through some transition state. And our energy diagram will look something like this. Now, when we take a look at this energy diagram, can we identify what the rate determining step would be? Remember, we consider how fast the reaction is. We need to consider its energy of activation. So for the starting material to go up to the transition state here, energy of activation 1. And for the carbocation to do its reaction, it starts at a high energy. So it's a very short path to go to the next transition state. We would call it energy of activation 2. And so this is our slow step. That's our rate determining step. Rate determining step is that that endothermic reaction where we're just breaking a bond and forming that high energy carbocation intermediate. Let's see if we can figure out what the transition states will look like. We have 2 transition states. Every step has its own transition state. So what's happening in our first step of the reaction? Remember, a transition state has partial bonds, partial charges. That first step is simply we're breaking that carbon-halogen bond where our leaving group is leaving. So because we're starting with butyl-bromide in this case, we're going to be breaking that carbon-bromine bond. It's going to be shown as a partial bond because it's breaking. And do we have any partial charges? What does it look like after this step? After the step, the leaving group is going to be bromide, Br minus. So we have a partial minus here. And after the leaving group leaves, our carbon is going to be a carbocation. So we have a partial positive here. So as that bromine is leaving, it's pulling its electrons toward itself. So there's a negative charge building up on that leaving group and a positive charge building up on the carbon that's going to ultimately lose those electrons and become a carbocation. So that's our first transition state. What does our second transition state look like? Well, our second step is our carbocation combining with the nucleophile. So in that step, we are going to be forming a new bond. And our nucleophile in this case was this guy. And so he's now going to be forming a bond to the T-butyl group. He came in as an O minus, but he'll be neutral in the product. So he's losing his charge as he's sharing those electrons to form the bond with the carbon. And this is now going to be losing its positive charge as it's gaining those electrons. It's gaining back its fourth bond. And so that's our second transition state for the second step of the SN1. What can we do? What can we know about the stereochemistry of the SN1? What happens if we have a chiral carbon, a leaving group on an asymmetric carbon that undergoes a SN1 substitution? What happens to the stereochemistry there? Remember SN2? We saw the stereochemistry. That was the backside attack mechanism. So we saw the stereochemistry got inverted, right? What happens in an SN1? Well, the way we describe an SN1 reaction is we describe it as undergoing racemization. That's what we refer to when we describe losing stereochemistry. And that's because with this stepwise mechanism, we go through a carbocation, and the carbocation is achiral. So here we have a chiral starting material, okay? But once this leaving group leaves, this carbon now has just 4 groups around it. What hybridization do we expect for a carbocation? This is sp2 hybridized. It's planar. And any planar species has that plane of symmetry in it, so this is achiral. So now when my nucleophile comes in, the question is it going to attack the top face of that carbocation or the back face of that carbocation? And the answer is both. It's going to attack from both directions to give an equal amount of the two possible products. Let's take a look at a different perspective here. Let's twist this around on its side. We have a CH3 and a CH2 CH3, and our carbocation is sp2 hybridized, so it has this p orbital here. It has an empty p orbital, and it's that empty p orbital that that our nucleophile is going to attack. Here we have sodium iodide as our nucleophile, so let's bring iodide in here. And what we'll find is that it can attack from this face. Let's call this path A. If it attacked from this direction, that means that the iodide would be bonded off to the left. We still have our ethyl group pointing out and our methyl group pointing back, but they're going to be off to the right a little bit. Or it can attack the opposite face. Let's call that path B. And how does that product differ? Well, it's now going to have the iodide off to the right. And again, the ethyl is still out and the methyl is still back. So there are two possible pathways here leading to two different structures. What's the relationship of those two structures? Are they identical? They kind of look like mirror images, don't they? Are they superimposable? Nope, these are chiral centers. These are asymmetric carbons with 4 unique groups on it. So guess what? We just formed one with the R stereochemistry, the other with the S stereochemistry. The relationship of these two are enantiomers. And we're going to get equal amounts of enantiomers because the likelihood of the iodide attacking one face or the other face is statistically equivalent. So we're going to get a 1-to-1 ratio of the two possible approaches. And we have, so we'll get a 1-to-1 mixture of our two products. And we have a special name for a 1-to-1 mixture of enantiomers. What is that called? It's called a racemate or a racemic mixture. And that's why we describe this process as one that undergoes racemization, because even though we started out with a chiral starting material, we ended up with a racemic mixture product, a racemic mixture. We could also describe it as having 50% of the reaction went with inversion. This would, I know we're looking at it from different angles, but if you compare this structure, if you tip it over and compare it to your starting structure, you see that this is the one where the leaving group came in from the opposite face of the nucleophile came in from the opposite face of the leaving group. But this other one we describe as retention. This product has the same configuration as the starting material. So we get equal amounts of retention and inversion based on attack of the two faces of this achiral carbocation intermediate. So what have we seen so far for the SN1 mechanism? This was a stepwise mechanism via the carbocation. And knowing something about that carbocation then is going to tell us something about the rate of the reaction, because the more stable the carbocation, the faster the reaction. So the best looking SN1 reactions we can have are for the best carbocations, things like benzylic next to a benzene ring, allylic, or tertiary. And I think let's just review what benzylic means. Benzylic means that you are next to a benzene ring. Allylic means that you are next to a double bond. And then tertiary, of course, means that you have 3 alkyl groups attached to the carbocation. So those you should recognize as all very, very good carbocations. So these substrates would love to do SN1s if they had a leaving group in those positions. Okay, so these would be the fastest. And these are the best carbocations, fastest reaction. And tertiary, primary and methyl are poor carbocations and very, very slow or even no reaction SN1. Because we've lost that leaving group, we no longer know whether it used to be a wedge or a dash or where it used to be, so racemization occurs in that situation and we end up getting a racemic mixture of products. And another thing we'll find is that because the rate determining step simply was based on how easily the leaving group was lost, how easily that carbocation was formed, we don't need a strong nucleophile at all. In fact, most SN1 reactions have no strong nucleophile, and we'll talk about nucleophilic strength in just a moment. But very often the SN1 is simply reaction with a very weak nucleophile like a solvent when we use water or some kind of alcohol. Those are very common SN1 reactions. In those cases, we call the SN1 the solvolysis reaction because it's a reaction with solvent. And we'll take a look at that mechanism too. But before we do that, let's compare the SN1 and the SN2 and think about their requirements and see if, for the following reactions, can we decide whether an SN1 or an SN2 might be favored. Okay, we just saw the SN1 was the stepwise reaction. So let's put down here, let's make a little note up here. SN1, if you can remember one thing when you think about the SN1, if you remember the word carbocation, that's going to answer a ton of questions for you about the SN1. That's all about a carbocation. How about SN2? SN2 was the single step mechanism that was backside attack. So if you remember that the SN2 is about backside attack, that's going to explain a lot of things such as sterics. Remember, sterics are really important. That's another very good word to remember when thinking about the SN2 mechanism. Okay, so let's look at these various substrates. So we have a leaving group here. He's on a methyl carbocation. Let's think about SN2. Is SN2 possible with a methyl leaving group? Is backside attack good when you have a leaving group on a methyl group? It's excellent because there's no steric hindrance whatsoever. How about an SN1? SN1 means carbocation. Would this be a good carbocation if the chlorine just left on its own to give a methyl positive? Absolutely not, because we can't have, let's say, no methyl plus. Okay, so this substrate looks like it loves to do SN2 reactions. Do we have a strong nucleophile? If we want to do backside attack, you need to have a strong nucleophile. Well, sure, we have here KOH, which is hydroxide. So yeah, I think SN2 is going to happen. What does that product look like? We're simply going to replace our leaving group with our nucleophile. How about the stereochemistry? Can we see that inversion that's taken place here? Well, no, not in this case because it's just a methyl group. It's not a chiral center, so there's really no stereochemistry to show here. There's only one stereoisomer of this product, so we just draw it as shown. Okay, how about our next one? How would you describe the carbon bearing the leaving group? We have a tertiary alkyl halide in this case because we have 1, 2, 3 carbon groups attached. So tell me, how does that look for the SN2? How does backside attack look on a tertiary center? Remember, we need to think about sterics, and tertiary is way too sterically hindered. We're not going to be able to do the SN2. How about the SN1, though? Carbocation. Is tertiary good for a carbocation? It's excellent for a carbocation. So that looks good here. So what does our product look like? Well, our nucleophile now is iodide. Our leaving group is the bromide. So our product will replace the bromine with an iodine. Now tell me about the stereochemistry here. Do I need to be concerned with whether I put the iodine up here or down here or a wedge or a dash? No, because this is a symmetrical molecule. This is not a chiral center. So again, whether you draw it as a wedge or a dash, it would be the same molecule. So there's no stereochemistry to worry about in this particular case. How about the next one? This time our leaving group is on a secondary alkyl halide. Okay, so tell me about backside attack. Is backside attack okay for a secondary? It is actually. It's not great, but it's possible. So SN2 is okay. And how about being a carbocation? Would a carbocation as secondary carbon be acceptable? Absolutely. Again, not the best carbocation possible, but certainly stable enough to be formed. Secondary halides, secondary electrophiles are where we're going to have some of our biggest challenges because both mechanisms are going to be possible in that case. So we're going to have to look beyond, think about something else to decide which one is going to be favored. And now let's take a look at our nucleophile in that case. Tell me about this nucleophile. I have O minus. I know we haven't quite talked about nucleophilicity yet, but I see a negative charge. This tells me I have a good nucleophile. And so something that would love to come out and attack. So guess what? If an SN2 can happen, it will happen. It's a very good, it will be the major product. It's a very favorable reaction. And so let's, now it doesn't mean SN1 is impossible. You might get a mixture of some racemization, some carbocation formation here. But typically we're looking for a major product when we're doing predict the product. So in this case, we would go with SN1. I'm sorry, excuse me, SN2, the backside attack. So, okay, I'm going to be replacing my leaving group with the nucleophile. And tell me about the stereochemistry here. Here we do finally have a chiral center that we're dealing with. Our leaving group is a wedge. That means it's coming out toward you. So where does the nucleophile have to approach? At backside attack, it has to come from behind the molecule. So we need to draw that as a dashed bond here. It was the oxygen that had the negative charge, so it's the oxygen that's now attached to the carbon chain. Very nice. Okay, how about our last one? How would you describe the carbon bearing the leaving group in this case? It is a primary carbon, but it's not just primary. It is also next to a double bond. Primary allylic. So what do you think about primary allylic? SN2. SN2 means backside attack. Primary allylic good for that? It's excellent. Not only does it have very little sterics, remember this neighboring p orbital helps stabilize that transition state. So this is a great SN2. How about SN1? How about SN1? Primary, I know primary sounds kind of bad for a carbocation, but remember, because it is allylic, it is now going to be resonance stabilized. So this is also an excellent carbocation. So here's another case where we can have both SN1 and SN2. Let's look at our nucleophile in this case now, though. Our nucleophile is methanol. It is a neutral molecule. It's no longer negatively charged like we've seen most of our nucleophiles will have. And we'll learn very shortly that we would describe this as a weak nucleophile. And in a weak nucleophile, what do you think about that backside attack? You think a weak nucleophile is going to want to come out and attack? I don't think so. Okay, so the weak nucleophile means that the SN2 is not possible. So instead, what happens? We have an SN1. What does that mean? It means our leaving group just leaves on its own to give a carbocation. And so what product do we get from that carbocation? If methanol is going to add, this is the group that's going to add to it. We'll take a look at this mechanism in just a moment, actually. The OCH3 group is going to be what replaces the leaving group. We'll see how that mechanism happens in just a second. Okay, but there's something else that's interesting about this carbocation intermediate. Because it is allylic, it is resonance stabilized. And when we draw the other resonance form that's possible, we find that we have a different carbon, a unique carbon that is electrophilic. And my methanol, my nucleophile can add there as well. And that will give me a different product. And that product will also be formed. So in the case of a resonance stabilized carbocation, we need to take a look to see if those different resonance forms might possibly lead to a different substitution product, and in fact, sometimes that can happen, like in this case. So let's see what that mechanism looks like. I just showed that if methanol was your nucleophile, then you would end up forming this methoxy group, this OCH3 group. Okay, and this mechanism is going to be a little more complicated. It's going to be 3 steps. And this happens very often in the SN1, especially if your nucleophile is, like we showed before, either water or alcohol. We called that solvolysis because it's reaction with solvent. And what happens in this case is a final deprotonation is required. So let's see if we can do the mechanism here. Looks like a substitution, right? Which substitution mechanism do you think we'll want to do here? Let's assume that we don't already anticipate that it's an SN1. How can you verify that it should be an SN1 mechanism? SN1 means carbocation. Because our leaving group is on a tertiary carbon, then that for sure tells me right off the bat I cannot do a backside attack. I can only do a carbocation. Okay. Furthermore, I have a weak nucleophile. So that also tells me that I can't do an SN2 and would have to do an SN1. So SN1 means carbocation. How do we get there? Our mechanism, our leaving group leaves. Right? If there is no nucleophile that can come in and attack, leaving group just leaves on its own to give a carbocation. That's never going to be our final step. Our carbocation is a great electrophile, so it looks around for a nucleophile that it can react with. And what nucleophiles do I have in the reaction? Well, actually, I just made bromide, so what we can note here, this is a good thing to note, is this mechanism is going to be reversible. This is an equilibrium that we have. The bromide can leave. It can come back in. So that would be possible. But if methanol is our solvent, that means that methanol is surrounding every species in the reaction mixture, including the carbocation. So actually, statistically, it's more likely that methanol is going to be the nucleophile that's going to react. Now, why not use methoxide? Wouldn't it be great to use methoxide, CH3O-? Because I want to add just an OCH3 group. Wouldn't it be great if I could just use a CH3- and then I'd be done? Well, that would be great, but what's the problem? Take a look at your reaction conditions. Where do you see that CH3O- has been added? This is not an ionic compound. We can't just lose that proton. This is not a salt. This is a covalent molecule, and the molecule must be used as a whole. Okay, so methanol is the nucleophile. So I have a new bond between oxygen and carbon. And what else is on this oxygen? It has still has a hydrogen and a methyl. Does it have any lone pairs? It had two, but one is now used. That's these two electrons that are being shared as a bond. So it still has one lone pair left. And how about a charge on that oxygen? Let's count. We have 1, 2, 3, 4, 5. Oxygen wants 6. So it's missing an electron. This is an O+. So here it is. We did our two-step mechanism, right? We lose our leaving group. And then step 2 is nucleophile. We add our nucleophile. We did our 2 steps, and we're not done. We're not done because this does not look like a stable molecule, does it? Does oxygen like having a positive charge? No way. So what we have to do is we have to do something to get rid of that positive charge. We know that oxygen wants to have 2 bonds, 2 lone pairs to be neutral. So which of these bonds can it lose? What group can it lose? Well, it's this proton that can easily come and go. We want to lose that proton. We call that step deprotonate. When you lose a proton. And something is going to come in and deprotonate. You could just say B ... as some kind of generic base. But again, who's most likely to do this deprotonation? It's going to be the solvent because it's the solvent that's surrounding everything. So I typically use methanol as my base. A lot of textbooks will come around and use this bromide as the base to kind of tidy things up. Because your other product that you're forming here, when you balance your reaction, your other product that you're forming is HBr. Okay, but whatever species you use, something is going to come and take that proton and then leave those electrons behind. Okay, proton transfer reaction, always 2 steps. 2 arrows. Grab the proton, leave the electrons behind, and now we have our neutral product. Okay, so this is going to be a little more common for an SN1 because usually our nucleophile is not something negatively charged. Usually our nucleophile is neutral. So after it adds to the carbocation, it now will have a charge, and we have to do a 3rd step to get rid of that charge. Let's talk about one additional complication we might have with a carbocation, and that is the fact that it can undergo something known as a rearrangement. Let's take a look at the following substitution reaction. I have a leaving group, and it's been replaced by a nucleophile, but take a look at where that nucleophile has come in. This was the carbon that was bearing the leaving group. That carbon is not the carbon that received the nucleophile. What's happened is the carbocation intermediate that's involved in this reaction has undergone a rearrangement. Let's go see what that looks like. First of all, once again, let's confirm our mechanism. Does this look like it should be an SN1 mechanism? Could it be an SN2? Well, our leaving group's on a secondary carbon. That's okay for an SN2, but tell me about your nucleophile. This looks like a pretty weak nucleophile because it's neutral, it's stable. So we're not going to have an SN2. Instead, the only thing that can happen is our leaving group can just leave on its own. So let's do that. The bromide can just leave. You can show that leaving if you want. I often don't show leaving groups after they left, so forgive me if your instructors like to see that. You need to get into that habit then. And I lose my leaving group and I form a carbocation. Now what happens here is this molecule undergoes a rearrangement where this carbon here with the positive charge is missing electrons, it's unstable. It looks next door and sees this carbon hydrogen bond with 2 electrons, and it steals it. It takes it. This hydrogen picks up and moves with its 2 electrons and shifts over to the next carbon. We call this a 1,2 hydride shift. We call this a 1,2 hydride shift, and let's see what the result is of this movement. So the hydrogen is now going to be attached to the next carbon over. So this carbon is happy. He now has 4 bonds again. But what about this carbon? This carbon just lost that hydrogen, so it now only has 3 bonds, and our carbocation is now in a new position. Now, as you can see, the way I've drawn this this equilibrium and the major product that's observed is this is a pretty favorable rearrangement. This is a pretty favorable equilibrium moving in the forward direction. So why is that? Why do carbocations undergo rearrangements such as these? Well, how would you describe this first carbocation? What kind of carbon it is on? It's on a carbon that's attached to 2 other carbons. We would call it a secondary carbocation. How about the new carbocation after the rearrangement? The positive charge is now on a tertiary carbon, so we call this a tertiary carbocation. And which one is more stable? The tertiary. The more alkyl groups you have, the more stable. So, this is why rearrangements occur. This is why we need to be on the lookout for arrangements. If there is any way for a carbocation to rearrange itself to relocate the positive charge to a more stable center, it will do so. Okay, so we need to be on the lookout for that. This process is called a rearrangement, and I want to be very careful to point out that it is not resonance, because we just saw an example where a positive charge moved, right? When it was an allylic carbocation. Remember, resonance is just moving lone pairs and pi bonds. No atoms move. You're just shifting around electrons and p orbitals. Here, we've changed the arrangement of the atoms. We've broken bonds and formed new bonds. So this is definitely not resonance. Be careful with your arrows here. This is an equilibrium. A rearrangement is how we would describe it. Okay, and so this is the carbocation. This tertiary carbocation is going to be the one that we have in highest concentration. So where do we go from here? Well, this is an electrophile, like all carbocations. So let's look around for a nucleophile. Water is our solvent. Water is what we have all around. So water is the nucleophile that we're going to use. And what happens to what does that product look like? Let me just combine these 2 hydrogens now together. So we just formed a new bond between carbon and oxygen. What's on this oxygen? Still has the 2 hydrogens and lone pairs. It had 2, but once again, this lone pair is now being shared as the bond. So we get an oxygen with 3 bonds and a lone pair. This is an O+. 1, 2, 3, 4, 5. Oxygen wants 6. Okay, so very good. We did we lost our leaving group. We did a rearrangement. We added our nucleophile. We're still not done because we need to get to a neutral product. So how do we get to this final product? We just need to lose one of these bonds. And so we could bring water back in as our base and deprotonate as our final step to get back to the neutral substitution product. Okay, so rearrangement, something to be on the lookout for anytime we have a mechanism involving a carbocation. So far, the only example of that is an SN1 substitution reaction. Let's see one more example of a carbocation rearrangement. We saw an example where a hydride, a hydrogen, picked up and moved with its 2 electrons. It turns out that also alkyl groups can shift. Carbon chains can shift. And so let's see an example of that. Here we have a leaving group. Now, if ethanol, ETOH, was our nucleophile, what group ends up adding and replacing the leaving group? Let's see if we could predict the product here. If I asked you to predict the product of this substitution reaction, you would replace that leaving group with what? Would it be an OH? No, this ethyl group isn't going to disappear in some mechanism. And OH is what you get when you have water as your nucleophile. When you have ethanol as your nucleophile, then it's the ethoxy group that's going to be in the final product, in the final substitution product. Okay, and that looks like a good idea, but unfortunately that's not the product that's observed. The actual product that's observed is this one, where now not only is the nucleophile on a different carbon from the leaving group, but my carbon backbone, my carbon structure is actually different. So this clearly must be some kind of rearrangement involving a carbocation. And let's see how that looks. So once again, our leaving group just leaves because we have no strong nucleophile to kick it out. So we have a 5-membered ring with a positive charge here. Let's draw on these methyl groups here. Instead of a line drawing, let me draw them in as CH3s. And once again, our carbocation, electron deficient, looking for some way to stabilize itself. It looks around and it sees this carbon with its electrons, and this entire carbon group, this methyl group, picks up and shifts over. We call this a 1,2 methyl shift. 1,2, just because it's starting on one carbon, it's ending up on the very next carbon. So a 1,2 methyl shift. Because it's a methyl group in general, you could just call it an alkyl shift. And now let's see what we have as a result. This carbon now has the methyl group attached. The top carbon still has one methyl group attached. And what happened to my carbocation? It's now going to be on this top carbon. It used to have 4 bonds. Now it only has 3 bonds. And so this is another example of a carbocation rearrangement. And now my ethanol, I'll draw out ethanol so that we know what that abbreviation is standing for. Our ethanol is our nucleophile. It will attack at the new location of the carbocation, followed by deprotonation. I won't fill out that entire mechanism. That would be good practice on your own. But eventually we'll get to this rearranged substitution product. We also get some very interesting reactions where this rearrangement involves a ring expansion to alleviate some ring strain. You'll see all sorts of very interesting examples of carbocation rearrangements. And not only can you have one of these rearrangements, but then that new carbocation intermediate can continue rearranging, and your carbocation can end up in all sorts of interesting places. So anytime we're doing a mechanism with a carbocation, we want to be on the lookout for these rearrangement products. Now let's talk a little bit more about the leaving group that's involved in both the SN1 and the SN2. Requires that it's a nucleophilic substitution of a leaving group. And what I alluded to in the beginning is that weak bases are things that make good leaving groups. And way back when we talked about acids and base strengths, what we look for to be a weak base is we looked for something that was going to be stable. So really what we're just looking for is a species that's stable on its own. So things like halides, not so much fluoride for an SN2, that's a pretty lousy leaving group, but chloride and bromide and iodide are all good leaving groups. Typically iodide is the best leaving group. Meaning it's the most stable leaving group. Why would a negative charge be more stable on an iodine than a chlorine? What's the difference between chlorine and bromine and iodine? You get bigger and bigger and bigger. So the iodide, remember, is larger, and so that negative charge is more delocalized on the larger surface area. So it's a large, delocalized negative charge here. So alkyl iodides are very hot electrophiles, really love to undergo substitution reactions, but bromides are fine and chlorides are as well. So we can use leaving group ability as a way to predict whether or not a substitution reaction is going to be favored. So let's take a look at the following substitution reaction. Here we have methanol reacting with sodium chloride. Let's get rid of that sodium right away and just focus in on the reactive species. We have Cl minus going to chloromethane and hydroxide. Okay, so this forward reaction can be described as a substitution, right? You used to have OH and it's been replaced by the chlorine. And the reverse reaction can be described as a substitution. You used to have a chlorine and now the OH has come into it. So let's compare the two potential leaving groups, okay? And because it turns out that the best substitution reaction has the best leaving group leaving. So when we compare our two leaving groups, chloride and hydroxide, which do you think is the better leaving group? Which of these would you describe as a very stable, weak base? The chloride, of course. The halides are what we've been seeing as great leaving groups. This is a great leaving group. Remember, it's a weak base. And hydroxide is a poor leaving group, very poor leaving group. This is a strong base, right? Most students remember from their general chemistry days that hydroxide, sodium hydroxide, is an example of a very strong base. So this is not stable. This is very reactive. That makes it a very poor leaving group. So which reaction is the favored reaction? Which is the reaction that has chloride, the good leaving group, leaving and getting replaced by a nucleophile? It's the reverse reaction that has the leaving group getting displaced by the nucleophile. This is a great leaving group on the carbon, where this is not a leaving group on the forward reaction, is no good. Okay, so in this case, the reverse reaction has the better leaving group. And therefore is favored. Okay, and is that something that would make sense? Would we rather have this combination of products? Yeah, if this is more stable, this is a weaker base, we're always going to be favoring more stable products, more of a favorable reaction. So that's what we're going to be looking for. So we could say that the best substitution reaction, it's the reverse reaction that has the delta H that's less than 0, the delta G that's less than 0. When you have the stable products for the reverse reaction, of course the products for the reverse reaction are drawn here on the left, that's going to be the one with the, that's going to be more favorable. Now because this is an equilibrium, when we describe this reaction, when we say that the reverse reaction is favored, remember our KEQ expression. KEQ is always the concentration of products over the concentration of the reactants. And so how would you describe KEQ for the given equilibrium? If the reverse reaction is favored, these starting materials, these reactants are the ones we're going to have in the highest concentration. These are the most stable. So that makes this the higher number. So KEQ is going to be less than 1 for this substitution reaction. So anytime we have an alkyl halide, that's typically going to be a very good substitution and very favorable because it gives a very stable halide leaving group. Now we just showed how hydroxide is a poor leaving group because it's so unstable, it's such a strong base, but there are some strategies that will make it better. It is possible to do a substitution reaction starting with an alcohol. Starting with an OH on a compound. And there's two methods for this. The first method is you can add a strong acid. You can add a strong acid. So HBr, HCl, HBr, HI, those are all very strong acids. These work well in this situation. And what happens is when you add an acid, it protonates the alcohol, and then a reaction takes place. So, for example, let's take a look at the reaction we just saw was this one. We said, what happens if methanol reacts with sodium chloride? This is the one where we said the reverse substitution would be the favorable one. So here we would say that there's no reaction here. Hydroxide is too poor of a leaving group. Chloride could never displace it, either SN1 or SN2. Doesn't matter which mechanism we're looking at here, because now we're just looking at the energy of the starting materials to products. That doesn't matter the mechanism you take to get there. However, instead of using sodium chloride, which means you just have Cl minus, if instead we use HCl, okay, the difference here is HCl has both the acid part and it has Cl, then you do get a substitution reaction take place. You can replace the OH with the Cl. So how does that work? Let's see how HCl could affect a substitution on an alcohol. Okay, and what happens is, as usual, every time we see HCl, HBr, HI, H2SO4, all those guys, those strong acids, we know they're strong acids. That's the very first thing they're going to do is they're going to look around for a base. They're going to look around for someone to donate a proton to. So that, in fact, is the first step that happens. And our mechanism for that proton transfer is the same every time. We start at the base. We grab that proton. We leave the conjugate. And so we're going to protonate the alcohol. Okay, and what does that do for us? And that also gave us a Cl minus. Let's show that because we're going to be using it. What does that do for us? Why does protonating the alcohol make a difference? Because now, let's take a look at what's attached to that carbon now. Instead of just an OH, what do you have? You have a positively charged H2O. When this leaves, what leaving group would we be kicking out? We'd be kicking out water. Can you get more stable than water? That is an excellent leaving group. So by protonating, we make a great leaving group. And once you have a great leaving group, a substitution can take place. Now, is it going to be, let's think about that mechanism for a minute. It could be maybe an SN2. It could be an SN1. What do you think is going to be favored in this case? SN2 means backside attack. Is this a good carbon for doing backside attack? Great carbon. Very little steric hindrance. Okay, how about SN1? Do you think the water will just leave on its own to give a carbocation? Does that look favorable in this case? No way, not for a methyl group. So it looks like this is going to be an SN2 mechanism to do the substitution. So that means backside attack, single step, attack the carbon, kick off the leaving group, and we get our substitution reaction. Okay, the other product we're forming is water. So why was this substitution allowed to occur? Why is this overall a favorable reaction? Because water is incredibly stable. It's a very weak base. And that's what makes it a good leaving group. So that would be a favorable reaction. So that's one way to make an OH a good leaving group. Let's take a look at another strategy. Another strategy is making what's known as a tosylate. What we're going to do is we're going to react the alcohol with TSCl, that's called tosyl chloride. It's kind of an abbreviation. We'll look at these structures in just a second. If you take tosyl chloride and base, we replace the proton on the oxygen with the tosyl group, with the we just abbreviate TS. And this is called a tosylate. This is called a tosylate. And again, like just like a halide, this OTS group is a great leaving group. And so once you have converted an alcohol to the tosylate, you can now react this with any nucleophile you want. It can either do an SN1 or an SN2, depending on your carbon chain that you're dealing with, and you can get a substitution take place. The product you're kicking out is TSO minus, and this is a great leaving group. So let's take a look at what this tosylate looks like. The TS abbreviation stands for this part of the molecule. So tosyl stands for paratoluene. Toluene is when you have a methyl substituted benzene ring like this. So it's paratoluene sulfonyl is what the tosyl is short for. So if you just have a chlorine here, that chlorine can get displaced by the alcohol group. Now that mechanism kind of looks like it might be a SN2, but it's not as simple a mechanism like that, so I'm not going to talk about the mechanism for that substitution. But what happens is you attach this tosyl group onto your oxygen, and then that now, with the oxygen, is what makes TSO the leaving group. So this is the same as this structure. We have a CH3OTS, we have CH3OTS. And what would happen if this saw a nucleophile? Well, we think of this big whole ugly thing as our leaving group. So let's say we want to do an SN2, it attacks the carbon, kicks off the leaving group. There it is. So that gives me my substitution product. And what does the tosylate TSO minus look like? Well, we have our tosyl group, SO, double bond, O minus. So this is our leaving group. Why is this more stable? This is a good leaving group, so it must be pretty stable. Why is this more stable than hydroxide? We said hydroxide was a lousy leaving group because there's such a strong base. Here's another O minus. Why is this one more stable? Can you see what the difference is? Is there any chance for resonance stabilization here? Absolutely. This O minus, this lone pair, is allylic. And so it can be distributed up to this top oxygen, this bottom oxygen. In fact, all three oxygens share it equally. So it's very delocalized. It's highly stabilized by resonance. So tosylates are really a great strategy for taking an alcohol. Alcohols make very good starting materials. We have a lot of those available, commercially available. So these make very good starting materials, and so it'd be very useful to be able to reliably turn it into a good leaving group. And tosyl chloride is one example of an application of that. So let's try a synthesis problem. Let's do some organic synthesis. Where let's say we wanted to synthesize this molecule, and so starting with this alcohol. And so our challenge is provide the reagents necessary to transform the given starting material into the desired product. So these problems are described as transform reactions, and really we're just asking for the reagents needed. Very often more than one step is going to be needed to do this. So, okay, I want to get rid of the OH. I want to put in an iodide. So how about I just use sodium iodide? Why can't I just use I minus and do an SN2 reaction? Have the I minus just kick out the leaving group. What's the problem with that? Who would your leaving group be in that case? The leaving group would be hydroxide. Is hydroxide a good leaving group? No way. Okay, so our challenge here is that this is not a leaving group. So if we want to do a substitution, we need to remedy that. Okay, so one strategy we can have for that is instead of using sodium iodide, we could use hydrogen iodide, HI. And what's the difference in that case? Now this is a strong acid in addition to being a source of the iodide nucleophile. So we know we're going to protonate first and make the good leaving group that could then be displaced by the iodide. So just a choice of different reagents in this case will enable the substitution reaction to take place. What was the other strategy we saw for making the OH a good leaving group? The other strategy was reaction that converts the OH to an OTS. If I had an OTS there instead, then that would also be a good leaving group and allow for a substitution. So what were the reaction conditions here? We know we need this TS group, and we need something on the TS group that can be replaced with the oxygen. So it's called tosyl chloride, TSCl. And you'll notice in this reaction we're going to lose that chloride. We also need something to deprotonate that proton. We're going to lose HCl, so we need some kind of base in this reaction, usually pyridine, or very often pyridine. So it's very common to see the reaction conditions as tosyl chloride pyridine. You might get used to working with that. Okay, but either way, once I have my tosylate, now it would be simple to convert that tosylate to the iodide. We have our leaving group. All we need is the appropriate nucleophile. So now we can come in with sodium iodide and expect the SN2 to take place to displace our good leaving group. Okay, finally, let's talk about what it takes to be a good nucleophile. We've been using nucleophiles in both the SN1 and the SN2 mechanisms to replace our leaving groups. Okay, and let's just talk about a few factors that we've really already come across. One thing, remember a definition of a nucleophile back at the very beginning. The nucleophile is something that is electron-rich, seeking an electron-deficient species. So the more electron-rich you are, the better the nucleophile. So let's compare. Here we have, this is called methanol. This alcohol with the methyl group here, this is methanol. Here we have a protonated form of methanol, so there's a positive charge. Here's a deprotonated form of methanol, so there's a negative charge. We call this methoxide. When you have a methyl and an O-, it's called methoxide. Okay, and so the more electron-rich you are, the better the nucleophile you are. So methoxide is described as a strong nucleophile. Methanol, because it's neutral, it's stable, still can be a nucleophile, still has lone pairs, but this is described as a weak nucleophile. And how about this species? Still has a lone pair, but because it already has a positive charge, there's no way it's going to want to share those electrons with something else and have a double positive charge. So we would describe this as not a nucleophile. So it could be neutral, or it could be negatively charged. And we could even do like a double arrow there because there's such a huge difference there. And what kind of mechanism of the substitution reactions, what kind of mechanism do you think would be suitable for something like methoxide? If you have a strong nucleophile, what reaction? Maybe backside attack? I think backside attack. So this is good for the SN2. We'd love to do the SN2. Okay, but methanol now is neutral, it's stable, it's not a good nucleophile, so it wouldn't do the SN2. So this is something that would be good for an SN1 reactions. If I had a carbocation, then methanol would be a good enough nucleophile to attack that. So we already saw a few examples where we made this distinction between them, and that will be something that we'll do in the future as well. So really, most good nucleophiles, if you take a look at nucleophiles, like we've seen RO- and HO-, we saw cyanide is a good nucleophile, N3-, we'll see. A lot of the nucleophiles we'll see X-, so we could have a halide being a nucleophile. Most of them have negative charges, okay? The exception to this are the amines, R3N, and the phosphines, R3P. If you take a look at the periodic table, phosphorus is right there underneath nitrogen. And so these guys, even though they're neutral, but they are strong nucleophiles. And they are great for doing the SN2. And we saw an example of that when we had ammonia did an SN2, even though it ended up having a positive charge in the product, that was just fine. So that's because these are pretty electropositive. They're very happy sharing their electrons. And so these are, when you see an amine or a phosphine, that's something that you should know that an SN2 is quite possible. And then finally, how about some periodic trends for nucleophilicity? If we move across a row, we'll see that we decrease in our nucleophilicity. And so ammonia, we just saw, actually, we said ammonia is a very good nucleophile, loves to do an SN2, but water is a pretty weak nucleophile and wouldn't do an SN2. And so we've seen an example of that trend, and that's going to be a general trend. Ammonia is described as a strong nucleophile, and water is described as a weak nucleophile. Okay, and what's the difference there? What's changing as you move across the row in the periodic table? It's the electronegativity as we move closer to fluorine. So, because oxygen is more electronegative, than nitrogen. What does it mean to be electronegative? It means you pull electron density toward yourself. So that means oxygen is holding onto its lone pair of electrons very tightly. Oxygen holds onto lone pair tightly, not willing to share them. Okay, that means the nitrogen is a better nucleophile. It's more willing to share those electrons and form a bond with the electrophile. Okay, and once again, just a little reminder, this is one of those facts of organic chemistry that's going to pay off knowing down the road, is that nitrogen is a great nucleophile even without a negative charge. In fact, when you put a negative charge on nitrogen, it's too unstable to handle a negative charge, and it doesn't want to be a nucleophile then. It'll end up being a strong base instead. So for it to be a great nucleophile, we just have a neutral nitrogen, and that would be excellent. The last trend in nucleophilicity is looking down a family, and this one actually is not so clear-cut. It can depend on the solvent. There are things you could do to change this trend, but one thing that is very common is that as you move down a family, you will see an increase in nucleophilicity. And remember we just talked about what happens as you move down a family, you increase in size. And so what we say here is that I- is larger, and as a result, it is more polarizable. It is more polarizable. To be polarizable means that it has this huge cloud of electron density. It can kind of stretch that electron density, reach it out toward an electrophile, start to form a bond. That's going to make it a faster reaction, a better reaction. And so therefore, iodide is the better nucleophile. Large nucleophiles are good nucleophiles. Again, that explains the nitrogen and the phosphorus. The phosphorus is bigger, so phosphorus is an excellent nucleophile and loves to do the SN2 reaction. So that wraps it up for substitution reactions. Hope to